So we now consider the change of variables formula in the case where we have a general transformation and not necessarily an affine transformation anymore. So for this, let us consider two open sets in Rn, U and V, and a map F from U to V that is a C1 diffeomorphism. And by this, we mean that F and the inverse. So it is assumed that F is bijective so that this inverse exists. And the inverse maps from V to U are continuously differentiable. So here C means continuous and 1 refers to the order of differentiability. And we only need the derivative to be continuous. If I have a function, say f, I should say g, which is either non-negative on v, and with respect to the Borel measure, or it is integrable over v with respect to the Lebesgue-Borel measure, then the integral over v of g is the integral over u of g of f of x times the determinant of the Jacobian of f at x dx. So as I said, dfx here is the Jacobian or Jacobi matrix of your function f. Let's say since it maps into a subset of Rn, so it has n components, and the Jacobian is the matrix where we take the ith partial derivative or the jth partial derivative of f sub I j from 1 to n, evaluated at x. So this is an n by n matrix. So before we prove this, take note that we get the affine change of variables from this formula, because if f is defined in this way, mx plus a, then you can easily see that the Jacobian is m. So the Jacobian is a constant n by n matrix. This leads to the affine transformation or affine change of variables, which was presented in the previous lecture. However, we stated this affine change of variables as a start, since we will use this formula in the general case. here, again, we will show this in the case where G is a characteristic function on some rectangle. So R here, so in the n-dimensional case, we have an open cell. Once you establish the formula in the case of characteristic functions, you apply the Lebesgue-du-Bois-Reymond strategy, and the uniqueness of sigma finite measures. Here, we would like to note that cells in V generate the Borel sigma algebra in V. So it is enough to consider open cells in V, since these cells generate the Borel sigma algebra on V, and you apply our uniqueness theorem for sigma finite measures to conclude that this formula is also valid for any Borel subsets of V. Therefore, in particular to characteristic functions over Borel sets in V. Okay, so let us emphasize what we would like to show. So replacing G by the characteristic function, we need to establish the following. So this would be the left-hand side, and the right-hand side would be as follows. Okay, however, take note that this one, as before, is nothing but the characteristic function of the inverse image of R. So therefore, this need to show is equivalent to the following. The integral over R, okay, dy, by the definition of the integral over a set, over a measurable set. And this would be the integral over f inverse of R of the absolute value of the determinant of the Jacobi matrix corresponding to F. So this is what we are going to establish in the succeeding discussions. So the strategy is to consider the following. So first, let us construct or consider the cutoff function or I should say the plateau function rho, which is a mapping from Rn into R as follows. So rho is equal to the characteristic or the reciprocal of the Lebesgue measure of the unit ball in Rn times the characteristic function of the unit ball. So the unit ball here is the set of ball X in Rn having Euclidean norm less than 1. So to visualize, Let's consider in the case of a 2D. So suppose this is -1, this is 1. So the function is 1 on the open ball. So we have here a constant function 1, and then 0 elsewhere. Aha. So this should be 1/2. Since the Lebesgue measure of this unit ball is equal to 2. So here you can think of this as the area. You have an area 1 because the height is 1/2 and the width is 2. Okay. So what we do is to scale this and retain the integral or the area. And suppose this is 1 -1 over n, and this is 1 over n. So to have an area 1, we need to increase the height into 1 over 2n. Or I should say 1/2 n. Okay. So here we now have this height. And elsewhere it is 0. So again, the area is 1. So in the case of general dimensions n, take note that if I integrate over Rn, the function rho, say dx, this is the same as 1 over lambda n, the Lebesgue measure of the unit ball, times the characteristic function of the unit ball, d lambda n, and this is equal to 1. Because you need to take the measure of this, and since you have the same denominator, the Lebesgue integral will be 1. Now, the region on the right can be defined by scaling rho. So for each positive integer m, let us define the scaled rho sub m mapping from Rn to R as follows. So rho m of x is rho of mx. Now we need to scale this, so we have m to the n. And let's say let us replace the integer here by m. So I should have a factor m to the n. So in n dimensions, we need to scale each height by or each dimension by m. Well, you can easily see that, let's say, if you integrate this, okay, and then changing variable, the variable x to y at this point. So this is the same as integral r to the n, m to the n, rho mx my dy. So here we apply our affine change of variables. So what we get is what 1 m to the n mn rho of x dx. So this will be cancelled, and we already know that the integral of rho is 1. So this scaling preserves the Lebesgue integral to be 1. Also, take note that rho of m of y is 0 if and only if, okay, rho of my 0, and this is equivalent to, okay, so take note that rho is 0 outside the unit ball, so this is 0 if and only if the Euclidean norm of my is greater or equal to 1. That is, if the norm of y is greater or equal to 1 over n. So if you are outside the ball centered at 0 with radius 1 over m, and then rho sub m of y is 0. Moreover, we can see here that rho is continuous except on the boundary of the unit ball. So in the two-dimensional, in the one-dimensional case, I should say n equals 1, the boundary consists of 2 points, that's -1 and 1. In the two-dimensional case, you will have the unit circle and unit sphere in the case of 3 dimensions. So you have continuity except on the boundary of the ball. So here we consider the following integral indexed by m. So let's define I sub m as follows. So we have here the double integral of rho m f of x minus y times the determinant of the Jacobi matrix at f inverse of y. Dx dy. So you can think of this as your x, okay? So we can write this as follows. So we have an iterated integral. So rho m f of x minus y dx. Take note that here we have a variable independent of x, so we can factor that out. Okay. And we will concentrate or evaluate the limit of the integral of the inner integral. Okay, so let us at the moment define k to be the inverse image under f of the unit ball, or the ball at y, centered at y with radius 1. This, of course, contains the inverse image of the ball centered at y with radius 1 over m. Since here we reduced the radius. Okay, so take note that if we look at the integrand, this is 0 if and only if, as we said here, if and only if f of x, the argument of rho m, so the distance between f of x and y is greater or equal to 1 over m. That is when f of x is in the ball centered at y with radius 1 over m. It's not, okay, an element. Or equivalently, when x is not in f inverse b1 over m y. So therefore, our function, or this one, the integrand is 0 outside this ball, or inverse image of the ball. And in this way, we can rewrite this integral as integral over f inverse b1 over m. Since outside this inverse image of this ball, the integrand is 0. We can enlarge this a bit to k, okay? Just to have a set that is independent on m. Okay. Since here we just added a set where the integral is 0. Okay. So we now proceed. Let us take a y in R. By this we mean this y here. Okay. So given y in R, the fact that f is the diffeomorphism, in particular it is bijective, there exists an x naught in f inverse of R such that y is equal to f of x naught. We now apply an affine change of variables. So namely, we change x to, let's say, some variable w. More precisely, we have the following transformation. So inversely, w is equal to m times x minus x naught. So let us now consider this integral here. So the integral over k of rho m f of x minus y dx. So this is 1 over mn times the integral of, okay, so k will now be m k minus x naught based on this transformation rho m of f. Now x will be x naught plus 1 over m w minus, so y is equal to f of x naught dw. According to our definition of rho m, we'll have 1 over mn times m minus k minus x naught, m to the n rho of m times this difference dw. So you see here, this quantity or this factor will be cancelled, and we have, okay, so let us integrate over the whole Rn, and we multiply this by the characteristic function of this set. And then let us rewrite the argument in the following way. Divided by 1 over m dw. Okay, so this one tends to the identity or the constant function 1 as m goes to infinity, because you are the set is increasing. So this one increases to the whole Rn. According to the differentiability of f, this tends to the directional derivative. So that's the Jacobian multiplied by the direction w. Okay. Now applying the continuity, of rho, we therefore conclude that rho of this difference quotient so as m tends to infinity, this one goes to a rho of d of f x naught times w. So continuous function is a convergence of preserving, except, okay, when w, okay, satisfies that the norm of the directional derivative is equal to 1. So in other words, except when this is on the boundary of our unit pole, which is the unit sphere. Okay. Why? Because we said a while ago that this plateau function is continuous except on this boundary. So let us define, let's say, just set n to be the set of all points in Rn, wherein this norm for this directional derivative is 1. Then, since f is diffeomorphism, so this is bijective, and we know that the image of n under this bijective map, according to this, okay, is the boundary of the unit pole. Or equivalently, n is the inverse image with respect to this Jacobi matrix of the unit sphere, the boundary of the unit pole. So here, let us take the Lebesgue measure of n and substitute the previous equation However, this is nothing but the image measure with respect to this matrix. And we know that what this is equal to 1 over the determinant of the Jacobi matrix at x naught times lambda n. Okay. However, this is equal to 0. Okay. And this is in a previous, or it is an exercise in the previous chapters. So you can look at this. So this is 0. So therefore, this convergence is valid almost everywhere. Since the set of points where the convergence does not hold, that is precisely n, has measure 0. Now, you can verify that the assumptions for the Lebesgue-dominated convergence theorem are satisfied. Hence, the limit f inverse r from f of x, or I should say rho m, f of x minus y dx is the same as the Lebesgue integral over r to the n. Okay, so tracing back here, so this one is equal to this one, and in turn is equal to this one. So we can now interchange the limits and the integration, and you have the following. So m k minus x naught rho of m So let us simplify this. So if we take the limit, we said that here we have 1, and here we have the d of f x naught w. So that would be rho d of f x naught w. Well, this is valid since this is valid except on a set of measure 0, but then that will not contribute to the integral. Now we apply our affine change of variables formula, and you will notice that this is 1 over the magnitude of the absolute value determinant of the Jacobi matrix integral r to the n rho of v dv. So simplifying, and this is equal to 1, make the definition of rho, and x naught here is equal to, as we said, f of y. And based on this, or I should say, f inverse of y. And whereas that, going back to the notation here, so x naught is f inverse of y. So again, by the Lebesgue-dominated convergence theorem, the limit as m goes to infinity of im. So let us highlight this integral here. This is the inner integral here. So taking the limit and applying the Lebesgue-dominated convergence theorem, we perform this limit and then multiply this one. And that will be the following. So we have calculated here, this is the integral over r of 1 over the determinant of df f inverse of y Okay, so that would be precisely this one. Since the integral on the right is equal to 1. And take note that in IM we have another extra factor. Precisely this dy. Okay, so this will cancel. Hence, we have the following. The limit as m goes to infinity is the integral over r of dy. And going back to the first step, this would correspond to the right-hand side of this equation. How can we obtain the other equation? That will be done by interchanging the order of integration. In particular, if we apply the Fubini-Tonelli theorem, you can see that. Okay, so taking a look at the formula for IM, we interchange the order of integration. So we now have rho m f of x minus y times the absolute value determinant of df f inverse of y dy dx. So before we have dx dy, now we have dy dx. Let us simplify the notation for this f. Okay, so let us set this to be f of y. So let us define this to be f of y for simplicity. Since f inverse and its Jacobi matrix are continuous, and the determinant is basically a sum of product of the entries, so this function is also continuous. Let us apply the definition of a continuous map. So given an x in f inverse of r, that would be the variable corresponding to the outer integral, and a positive epsilon, one can find a delta, and in general this depends on epsilon and x in such a way that if the distance between f of x and y is less than delta, then the distance between the corresponding images under the continuous function capital F would be less than epsilon. This is nothing but the definition of continuity at the point x, or at the point f of x. Now we choose m, the integer m large enough, so that the ball centered at f of x with radius 1 over m is a subset of R. In this way, we can write the inner integral, namely this one, as follows. Then the integral over R rho sub m of f of x minus y, capital F of y dy, will be the same as the integral over this ball. Okay, take note that this function is 0 outside this ball, so it is enough to integrate over this ball centered at f of x with radius 1 over m. Okay, and then we add and subtract capital F of small f of x. So this is dy. So we need to correct that. We need to add that term. So here we have rho m f of x minus y dy times, okay, we can factor out this since this is independent of the variable of integration. And you can show by a transformation rule, or I should say by translation invariant of the Lebesgue integral, and knowing that the integral of rho m is 1, this is equal to 1. Let us denote the first integral by j. So here we now have f of x. So this first integral is denoted by a j. Okay, so if I let m be such that the reciprocal of 1 over m is less than delta for m greater than or equal to capital M, and this is valid because delta is positive, so we can take this capital M to be large enough so that the reciprocal is less than delta. So looking at the formula for j, or the expression for j, this is less or equal to the integral of rho m f of x minus y times the Euclidean norm f of y minus f of small f of x dy. And this is less than epsilon, since if y belongs to this ball, it means that the distance of y and f of x, that's the center, is less than 1 over m. For m greater than capital M, this would be less than delta. And you apply this statement here due to continuity. So therefore, we now have the following. This is less than epsilon since the integral of this over this ball is 1. So for all m greater or equal to capital M. So it must be proper to put a subscript m on j to emphasize its dependence on m. Thus, the limit as m goes to infinity of jm is 0 by the definition of the limit of a sequence. And in particular, okay, looking at the limit here, so the limit as m goes to infinity of this one, okay, so performing the limit, we will have the following. Since jm tends to 0. A final application of the Lebesgue-dominated convergence theorem, we end up with the following. So the limit as m goes to infinity of im. Okay, so look here. We take the limit we can now take the limit of the inner integral, and we know that the limit is f of capital F of f of x. So that would be the following. So this would be f inverse of r. The limit of the inner integral is this one, f of x dx. However, what is f of capital F of small f? So this is the determinant. So let us look at the definition. Okay, here, determinant of the Jacobi matrix of f inverse of f of x. So you replace y by f of x. And you can see that this is what? The absolute value of the determinant of the Jacobian at x. So f inverse of f of x is just x dx. So again, going back to what we have established. So we calculated a while ago that the limit of the integral Im is the integral of r, integral over r. We applied Fubini to interchange the order of integration. We have established that this limit is also equal to this one. The uniqueness of limits implies that the two limits must be the same. And this ends the proof of our claim. More precisely, going back to the previous discussions, this highlighted part here. So we have established this equation, and according to the beginning of the proof, if you apply the Lebesgue-Dubois-Reymond strategy, and then applying the uniqueness of sigma finite measures, knowing that cells in V, open cells in V in particular, generate the Borel sigma algebra, you now obtain this change of variables formula in the case of C1 diffeomorphism. So we will use this in the next lecture to derive the classical change of variables formula that we are using in elementary or basic calculus, namely the polar, cylindrical, and spherical coordinates.